Now we have to gauge fix the theory and see how we can simplify the equations. So I think you remember what you get in QED. You get equations of this form. Proportional to the source, which is invariant, and that's exact. It's not a lowest order gauge transformation, that's exact, but in Yang-Mills theories, non-abelian, that would be the lowest order gauge transformation. So, and then to solve that equation, this equation cannot be solved like that, because it's impossible to find a green function and invert the operator that acts on A. We'll see it many times like this, so no need to see it here, but precisely because of this symmetry, it's impossible to. So you need to fix the gauge, and the gauge fixing that you normally use is this. So you get rid of that term, and you get box A mu equal J, some constant depending on your system of the reference. And so let's do the same here. What is the most convenient gauge? It's called harmonic or dead-onder gauge. And it's similar to that of QED. And it reads as follows: partial mu phi mu nu minus 1/2 partial nu phi equals 0. So you could choose this equal to 0 only. You could put a constant here. But with this peculiar choice, it's like the Feynman gauge, if you know something about QED. So that's the most convenient one. We will see in a moment, because it simplifies the equations and it reduces that then to this form. So, but before that, why can we choose something like that? Observe that we have 4 gauge symmetries. It's not like in QED where you have one. In QED you have just one function, and so you can fix the gauge by choosing one condition on A, which has 4 components, because A mu has 4 components. But here you have 4 conditions. And so you can impose 4 conditions. And indeed these are 4 conditions, because this index nu is free. It's not contracted. You cannot impose more than 4 conditions. Let's see if this fixes the gauge, and actually we will also see whether this to the lowest order, so considering this gauge transformation, or there is a gauge, a residual gauge. So let's compute the gauge of variation of this condition and see what happens when it is 0. So the gauge variation of this. What is it? Well, the variation of phi mu nu now we know is very easy. You can also check that the variation of the trace is twice the divergence of C plus order phi. So this variation is partial mu times partial mu C nu plus partial nu C mu minus 1/2 partial nu times the variation of C, which is 2 times the divergence. The 2 goes away, and this partial nu divergence cancels this, which is also partial nu divergence. So you just get box C nu. This is the residual gauge. The same way as in QED, you might remember that if you check the variation of this gauge condition, that is box lambda, and box lambda equals 0 is a residual freedom to impose a gauge condition. But the residual gauge freedom plays a role that must be used in a specific way. So let's now use it. Let's now insert this condition into the field equations and see how they simplify. Now we will focus on the free field equations because we want to understand what gravity propagates freely. The waves, no sources. And in the free field limit, actually, because even if there are no matter sources, the gravity interacts with itself, and there are higher order corrections. But again, we do perturbation theory, so we have to start from the lowest order. So I thought I had copied this, apparently I didn't. So what we do now is to study the vacuum field equations to the lowest order together with the gauge fixing. What can we do? You see, that allows you to simplify every expression where phi is contracted, one index of phi is contracted with a partial, the index of a derivative. And that happens here. There are two contractions, actually. Here and here. The other terms have to be left there. So here you have eta, and instead of this, you can put one half partial, also, yes, you can write it like that. Partial mu phi mu is equal to 1/2 partial nu phi. So that is equal to 1/2 box phi. Then we copy this term. The last but one term will be 1/2 partial nu partial rho phi when we use the gauge fixing. And the last term will be actually the same because it's plus 1/2 partial rho partial nu phi, which is the same. So the last three terms cancel, and the second and the third give can be collected, and they give plus 1/2 eta nu rho box phi. That is equal to 0. Now we trace this equation. So you have minus box phi plus 1 divided by 2. The trace of eta is 4 box phi. And that implies that box phi is 0. Then you go back to this equation. If box phi is 0, box phi minor is 0 also. So you get your wave equation. So this is the gauge fixed free field equation. Box phi minor is 0. And you know what the solutions are, I suspect. So gravity propagates waves, gravitational waves. Now to study the helicities, the two propagated degrees of freedom, we have to move to momentum space. So box phi mu equals 0 will become what? K squared Fourier transform, which will depend on k equals 0. That implies that k squared is equal to 0. We can choose k mu with upper indices. We can choose what you want basically, but as long as k squared is equal to 0, we can choose two vanishing space components. And let's choose this one. Let's see. So this is the equation. And remember, we also have the gauge fixing conditions. So the equation we have already solved, basically, k squared equals 0, which is incorporated now in this choice. And now we can go back to the gauge fixing condition. So when you remember, if you want to keep track of the i's or the minuses, here they cancel out because everything is equal to 0. So here you will find this condition. Remember that sometimes k appears with lower indices and sometimes with higher upper indices, but we know how that goes. So we are using a metric signature which is plus, minus, 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 which is, by the way, not the one that is normally used in general relativity. But I will always use that one because I come from particle physics, and quantum gravity, we will see, will come from there. And what we are doing here is following the path of particle physics, so it's natural to use the same notation that's used in the standard model. Now we solve this condition with that k, and we will see that many components of phi mu nu are set to 0 by this condition, and the one which will survive will be the helicities. For example, Let's see what happens. Here we have 4 conditions. Let's see what happens with nu equals 0. Well, first let me see here. Here you see you have a contraction, mu and mu. And since we know k, we just have 2 components. K phi tilde 0 nu. When mu is equal to 0, and then you have mu equal 3, which is again k, and that is phi tilde 3 nu minus 1/2 k nu phi tilde. Now it's easier to check what happens with nu equals 0. You get k. This k, by the way, is not the same k that we used before. That k is not a k, actually it should be a kappa in the tech language. But here it's difficult to see the difference. But so now it's if you want, you can use p, but for waves normally you use k. So k, so it's a little bit bigger than the other k, which was a kappa. You have phi tilde 0 0 plus phi tilde 0 3, actually yes, minus 1/2 k nu, lower indices, that's k again, phi tilde. Because the first component is k. So k will always go away. You have a certain relation between the components. That eliminates one component. Nu equal 1. You have phi tilde 0 1 plus phi tilde 3 1. Here you have nothing because k doesn't have a 1 component. So for nu equal 1, you just have phi tilde 0 1 plus phi tilde 3 1 equals 0. Well, you have the same for nu equal 2 because it's the same structure. For nu equal 3, you have k, we can drop it because we know it will disappear. Phi tilde 0 3 plus phi tilde 3 3 minus 1/2. Well, the sign will not be important, but let's pay attention to the sign because even if we make a mistake here, the result will be the same. But anyway, this is k3. We're lowering this, so it's minus, which means that you have plus phi tilde equals 0. So phi mu is a symmetric, phi tilde mu is a symmetric matrix. It has 10 independent components. With these 4 conditions, we are losing 4 such components, and from 10 we go down to 6. The other 4 are lost by means of the residual gauge freedom. So now we have to impose something. We can impose something else. Let's see why. So let's use the residual gauge freedom. Which is so it was this with that. But in Fourier transforms, that's minus I k mu, C nu, tilde, minus I k nu, C tilde mu, with k squared C mu tilde k equals 0, which means that we can just use the same k that we have used so far because k squared was already equal to 0. So we can use a C tilde function of the same k, and let's see what we can do there. So this is something we can do. Let's check, for example, that this is really a gauge, a residual gauge. For example, we can check that these conditions will not change. Let's check, for example, that this condition doesn't change. You can do for all of them, but we already know they don't, but to see it explicitly is better. Let's see that this doesn't change. We replace 0, 2, minus 1, k 0, c tilde 2, k0 with lower index x is k. Then there is minus 1, k2, c tilde 0, there is no k2, the component 2 is 0. And then there is plus variation of phi tilde 3, 2, which is minus I k3 c tilde 2 minus I k2 c tilde 3, but there is no k2, and k3 with a lower index is minus k. With a lower index is minus k, so that is correctly 0. We don't need to do anything else because we are using already a function c tilde of the same k. And the other condition is already incorporated there. But now we can use this freedom here to impose extra conditions. Because this is invariant, but this is not. And if this is not, we can impose this equals 0, which will always also impose that equals 0 by the previous condition. So both will be 0. Phi 0 tilde 2. Same with phi 0 tilde 3. And the same with any component that does change. For example, let's see. Oh, okay. No, we have to keep track of what we are using. So we can impose phi tilde 0 to equal 0 using c tilde 2. We cannot use it twice. That's what we have to be careful about. We can impose phi tilde 0, 3 equals 0, and that forces us to spend c tilde 3. Let's see if we can use the c tilde 1 and c tilde, no, sorry, 0, 1, 0, 1, and 1 and 2 in our choice of k are the same, not 1 and 1, not 2 and 3. 0 and 3 instead are similar. Let's see what if we can do something with phi tilde 0, 0 and phi tilde 3, 3. Okay, 0, 0 means that we have twice the same k c tilde 0. So yes, we can impose phi tilde 0, 0 equals 0. We do it down here. So phi tilde 0, 0 equals 0 using c tilde 0. And phi tilde 3, 3, we have 3, 3 that just changes the overall sign. So you can also impose phi tilde 3, 3 equals 0 using C tilde 3. And now we have 8 conditions from 10 components, and we will remain with 2 independent components, which are the 2 helicities. So let's insert these. Let's see what happens. Let's build this matrix phi tilde mu nu, and let's see 0, 0 and 3, 3 are 0. 0, 2 and 0, 1 are 0. And so far we have this. Now we go back to the previous page and use the fact that we have imposed 0, 0, 3, 3, 0, 1 and 0, 2 equals 0. So 3, 1 and 3, 2 will also be 0. Three, 1 and 3, 2 will also be 0. Now, from the other 2 conditions, actually the signs are very important here, because you see, from the other 2 conditions you have phi tilde 0, 3 is equal to 1/2 phi tilde. And phi tilde 0, 3 is equal to 1 minus 1/2 phi tilde. Which means that phi tilde 0, 3 is 0 and phi tilde is 0, the trace. So let me write it like that. All of those are 0. Phi tilde 0, 3 and the trace. So phi tilde 0, 3 means this one, and it's 0. And then the trace. And the trace being 0 means that you will have something like that. And symmetry means that you have only 2 degrees of freedom. That is the matrix of polarizations of the graviton. And so we can study the polarizations of the gravitons. Basically, we have a 2 by 2 matrix with these current features. It's symmetric and it is traceless. And this you can write as a linear combination of 2 polarizations. You can define circular polarizations, you can define the kind of polarizations you want. What we use here are the eigenstates of the helicity, which are epsilon plus is equal to what? 1, I have to complexify the field, but then the same way as you do in classical, actually, electrodynamics, where I complexify often the electric field and the magnetic field. And epsilon minus is the conjugate. So A and B have to be real. Alpha and beta will be complex conjugates of each other. So that will be alpha plus beta. minus alpha minus beta, I alpha minus beta, and I alpha minus beta. And beta is equal to alpha star. So here you have basically the real part minus the real part from factor 2, you have the imaginary part. All entries are real, however. And why is this the correct polarization? Are these the correct polarizations? Because under rotation they transform correctly. So let us consider a rotation, which is a 2 by 2 matrix as well. Cosine theta, sine theta, minus sine theta, cosine theta, which will hand it to this. And how do you transform? This is a matrix, not a vector. So a matrix has to be transformed epsilon plus or minus go into what? R theta epsilon minus plus or minus R theta transpose or minus 1, whatever, it's the same. Let's compute what happens. So this is 1 plus or minus I plus or minus I minus 1. And then the inverse or transpose, the minus is there. Okay, let's make the first multiplication. You have cosine theta plus or minus I sine theta, which is e to the plus minus I theta. Then you multiply this by that and this plus that. So you have plus or minus I cosine. It will be plus or minus I theta. Plus or minus. You can check it because the sine part, okay, I should have first cancelled the other thing. Plus or minus I. Because this is cosine theta plus or minus I sine theta, plus or minus is plus or minus, and so you have a minus. You can go on, you will see that these are exactly eigenvalues. We built it that way, so basically the matrix is multiplied by e to the plus or minus I theta. So basically what you have is e to the plus or minus I theta, 1 plus or minus I plus or minus I minus 1. Now you can do the same there. You will find another e to the plus or minus I theta. Just do it for the first, for the second. So you get e to the plus or minus 2 I theta epsilon plus or minus, which means that the helicities are 2 and minus 3. So a graviton propagates 2 degrees of freedom with helicities 2 and minus 2. And if you want, for comparison, to check what happens in QED, to be sure, have been doing everything okay. In QED, you have polarizations that are not matrices, but vectors. Which is basically this vector, the first column. And there you just have one. It's a vector, so the rotation is this. But we have already calculated this. It is this part. We have already done that calculation. So in QED, what you have is helicity 1 and minus 1. That is what happens yes, we can write some arrow here. And that's it for the classical part. And on Monday we will be moving to the quantum part, little by little, with the propagator of the graviton. Let me just make a final comment. In d dimensions, what happens? We have worked out everything so far in 4 dimensions. And in d dimensions, vector d minus 2 helicities. Graviton d times d minus 3 divided by 2. Since we have 4 minutes, we can spend a few comments on, say, how this comes out from what. A mu, that is d components. Then you have 1 gauge freedom, that's 1 component. But remember that every time you have a gauge freedom, you have the same number of residual gauge that allows you to impose the same number of conditions. So basically you double the number of gauge conditions, d minus 2. And here the same, because G mu nu has how many components? 10 in 4 dimensions, but it's a symmetric matrix. So the number of components of a symmetric matrix is d times d plus 1 divided by 2, yeah, minus 2d. So d conditions from the gauge fixing. 4 in 4 dimensions, and d from the residual gauge. Let's see what happens here. 2d squared plus d minus 4d. Which is true for d larger than or equal to 3. So in d equal 3 you have no gravity. In d equal 2 you have no gauge fields. Gauge fields start to exist in d equal 3, but in d equal 3 they're a little bit too simple. There is only one component, not two helicities, one. Kind of strange. They look like scalars actually. They are dual in some sense to scalars in 3 dimensions. So this is to make the final comment. Life starts from 4 dimensions. There is little below 4 dimensions. Okay.